precisely near this critical point, this discrete model admits an approximate continuous description in terms of an effective action, which is the effective action of phi squared plus phi to the fourth scalar. And the interesting point that when you are at the critical temperature, the mass of the scalars has to be zero if you want to reproduce the properties of the discrete model. Essentially, if you want to reproduce the fact that correlation functions at the critical point have a very large correlation length. So now let me work in the limit where this array of spins is infinite, then in this limit, the correlation length also becomes infinite, in particular, much bigger than the lattice spacing. And so you see why you can approximate this discrete model with a continuum description. And you also see why the mass of the scalar has to be zero, because you want the correlation functions of this continuum theory to also have a big correlation length. So you don't want the exponential suppression that you would get in real space if the mass was not zero. And so, okay, this is the sketch of why we're gonna do what we're gonna do next. And next, we're gonna try to understand better what this operation, so this duality operation means, whether it's really a symmetry or not, so whether it's really sending you the model to itself or not. And finally, we're gonna make some speculations about what this symmetry means in the continuum. Okay, so as a full disclaimer, I should tell you that I'm far from being an expert on the topic. I always like to give at least one lecture on something that I didn't know before giving the lecture. So there are high chances that I'm not going to be able to answer all your questions. And in particular, I also have not yet answered all of my questions, which is the precise mapping of this operation in the continuum. I do have some ideas, but well, you will see this towards the end. All right, so but let's start with this discrete set of points in two dimensions, and try to find this dual description that I mentioned. So you're gonna think about an Hamiltonian that looks like this, where these angular brackets mean that I'm summing only over nearest neighbors. So for each point, I'm summing over its 4 neighbors. Well, then the partition function can be written as usual as a sum over all the possible configuration of spins e to the minus beta times the Hamiltonian. And let me define beta not as the inverse temperature, but as the coupling over the inverse temperature. It's more convenient in this story. And so what we're going to do next are some manipulations of these expressions that will show us the duality between high and low temperature. And this is the part that is very well known to our statistical physics colleagues, some of whom are in the audience. So, okay, well, I'm going to try to go quickly, but not too quickly, because not all of us have seen this before. For now, I'm just writing explicitly the Hamiltonian. Then it's easy to notice that this exponential of a sum can be written as a product of exponentials. And then I'm going to just use an elementary property, so the fact that e to the ax is equal to the hyperbolic cosine of x plus a, the hyperbolic sine of x, if a squared is equal to 1, to write down the expression in an equivalent way. And the ck, so c0 of beta is the hyperbolic cosine and C1 is the sign. So for now, I've done essentially nothing. But now, okay, you see, so this sum has only two components. So really here I'm writing something like the product of C0 of beta plus C1 of beta times sigma I, sigma j. So I can write this expression in an equivalent way as well. I still have the sum over the configurations, but now I can move out of the product over nearest neighbors this factor of ck if I keep track of the fact that there are as many of them as there are links in the lattice, right? So for essentially each pair of spins that I can take in the lattice, I'm going to have a factor of ck in this product. And so I can write that last piece as a sum over all the links now. So in this case are all the links in the lattice of a product over all the links. Let me say that there are f links in this lattice, and I haven't taken the limit of the lattice going to infinity yet, times the product over nearest neighbors of the two spins, which stays the same. And now let me call this k kij. Okay, so this k1 to kf and these kij's are the same thing. I'm just using this bad notation to remind myself that I can associate a k to each nearest neighbor. But here it's easier to write them as just a string instead of a matrix. At this point, well, we can rewrite this product here as a product over I times a product over J prime, where J prime are the neighbors of I, of sigma I to the kappa I J prime. Okay. And finally, well, this product over J prime becomes just a sum at the exponent. So this is a product over I of sigma I to some power, where this power is just the sum of this case for all the nearest neighbors of this point I. So it's a sum over 4 terms. So far, well, okay, as you see, it's just algebra. There is nothing illuminating, but I promise you that in a few minutes, we're going to learn something interesting. You just have to bear with me for a couple of more of these manipulations. Okay, so now I'm just going to plug back this in here. So I have the sum over the configuration sigma, the sum over the links k, the product over all these ck's, and now, well, I have the product over I of sigma I and I. Now let me go to the next left quarter. So now it's useful to move this sum over here, because since we have a single spin, this sum over all the configuration just becomes a sum over 2 numbers. I mean, so sigma I can be -1 or 1. And so if we do that, then the partition function, so going from here we have the sum over the links, the product of our cosines, hyperbolic sines and cosines. And then, well, we have the product over I of this sum And so the first piece stays the same. And here we have a product over I of 1 plus minus 1 to the ni. And so you see this is non-zero only when this ni number is even. So I'm gonna, well, so first of all, to stop, I don't know why I kept doing this all along, but I could have just written this as a product over links. I should have done it 3 steps before, but let me do it now. And then here I'm just going to write a delta 2 of ni. So this is a Kronecker delta mod 2. So essentially it's 0 if ni is odd and it's 1 if ni is even. Okay, now, okay, this was just algebra, but now comes a slightly more interesting part. So what I want to do essentially is to construct a representation of my lattice that always satisfies this constraint, so I don't have to keep track of it. And there is a clever geometric construction by Kramers and Vanier that does it. So if this is my initial lattice with my variable sigma, now let me build a lattice which is displaced by 45 degrees in each direction. So I'm going to put a spin in the center of every plaquette. Then, okay, the links in the old lattice are in one-to-one correspondence with the links in the new lattice. So let me call L the links in the old lattice and L star the ones in the new. So for each link in the old lattice, there is one in the new one that crosses it. So I can always associate, so let me call mu the new spins. I can always associate 2 spins in the new lattice to a link in the old one. So let me call this, I don't know, mu L star 1 and this mu L star 2. And now I want to choose a representation of the links, so of this case in the original lattice in terms of the spin variables in the new lattice. So these mu's are again objects that can take only 2 values. And it's not hard to show that if you choose this representation, again, this is just a choice of parameterizations of the links of the old lattice, then the constraint is always satisfied. So your ni was the sum over the neighbors of I of the links, of this case over the links. So for each point in the lattice, I was summing over these 4 lines. And in this representation, this becomes 2. So there is a 1/2 summed over 4 times, minus 1/2. Let me call for simplicity, the 4 spins around the site that I'm interested in, 1, 2, 3, and 4. So then I'm going to have this. And you can check that for any choice of values for the 4 mu's, this is always even. And so in practice, this construction satisfies my constraint. So in a second, I will show you how to get rid of the delta function. But before, let me mention an important point. So the important point is that this representation is redundant. So if you send all mu's into minus themselves, the case stays the same. you might be tempted to say that this is a symmetry, but it's not a symmetry. It's just a redundancy of the parametrization. So in modern language, you would call it a Z2 gauge symmetry. So you can explicitly keep track of this gauge symmetry by saying that mu by itself is not gauge invariant. So for example, computing correlation functions of this type does not make sense. So this object is not gauge invariant. You want to add some gauge field on this dual lattice. Okay, and the simplest, so this is the part that you would not see in the statistical mechanics textbooks, but it's the part that explains this line and the fact that the duality is not exactly a symmetry. So how do we gauge a symmetry on the lattice? How do we gauge a discrete symmetry on the lattice? So the simplest way is to use is to use not what we would do in particle theory in physics, not gauge fields, but objects that are more similar to Wilson lines. So let me start in the continuum, which for me is more familiar. So I can define an object like this, which now I'm going to explain in a second all its components. So let's say that I have a gauge symmetry in the continuum. The gauge fields are A mu, the generators are T. Then I can always write down an object like this. So I'm integrating the gauge field over some path C that goes from xi to xf. This P is a path ordering, meaning that if I parameterize the path in terms of some affine parameter S, I'm going to compute this exponential by expanding the exponent, and I'm going to put on the left side elements that have larger values of S. Okay. All these, in the end, we're not going to need all these details. The only point that's useful for us is that you can show relatively easily that this object under a gauge transformation transforms like this. Where this is the full element of the group. So it's again e to the I, the generators. And well, from here, immediately a useful application to the discrete case. So here, these objects can be defined over links. So I can write down some operator U going from site I to site J, which transforms exactly like this. So like GI, GJ dagger. Well, since we have a G at Z2, the dagger doesn't really make sense, but these G's are just really plus or minus 1. If we add a Zn, then from this transformation property, you see that the right object to write down, which is gauge invariant, is this one. Since we have a Z2, we can also forget about this stuff. And so really the correlation functions that make sense are objects like this. So the gauge invariant objects attach mu's to each other with some link field U or some Wilson line U, and it really means that I'm attaching mu to infinity with a series of links like this. Okay, and this is also gauge invariant. So in principle, if I wanted to be completely honest, I could put a U here in the middle to keep track of this. I'm not going to do it. So it's important to keep this in mind, but I'm not going to do it because I mean, you see immediately that locally I can always set u to 1 everywhere, locally at least. Okay, so all these details that I've given you are important only for the global properties of the system. There can be some objects that are topological that know about this gauge symmetry, but locally you will never know. I mean, you see it from here. So these transformations are plus or minus 1. U itself can only be plus or minus 1. You see it if you try to write down the Z2 equivalent of this. And so, I mean, I can just set it to 1 locally on every side by a gauge transformation.
Sorry, so I mean, you are not willing to gauge a larger group than Z2. Do we agree on that? Because if you want to do that, what I don't understand is that the mu are in a kind of fundamental representation of the group, and then you would have something like mu dagger, u mu. Otherwise, it's not an invariant.
Yeah. No, that's what I said here. So if you had a bigger group, you would put mu star or mu dagger.
Okay.
But yes. So here, so it's not okay. You could call it a choice, but for now, all I've done is construct this representation, and then I've noticed that this representation is Z2 gauge invariant. That's okay. Then okay, indeed. I mean, you can, especially in higher. I mean, then you can generalize all this story. I mean, there are also models with a Zn symmetry, and then indeed you need a dagger or a star. But for today we care only about Z2. Okay. All right, so let's now, okay, after all these caveats, let's go back to what we were doing before. So now I have these dual variables mu, and as I've already shown you, for each link in the original lattice, there are 2 mu's that you can associate to it in this representation. So in principle, I can replace the sum over k with a sum over mu. And the 1/2 keeps track precisely of the redundancy. So you have a double counting if you sum over all the mu's instead of all the k's. Then for the reason written here, I invite you to check, this delta always gives us 1. So in practice, this product becomes 2 to the n, where n is the number of sides in the 2 lattices. And finally, well, again, for what we've just shown here, since there is a new link crossing an old link, so they're in 1-to-1 correspondence, I can also replace the product over the old links with the product over the new links. And so in practice, if I do all 3 of these things, I'm going to have 2 to the n minus 1 times sum over mu of a product over the links in the new lattice of C of this. So 1 minus mu L star 1 mu L star 2, the 1/2 of beta. And now we are essentially done. Let's see. So now we're starting from that last expression up there. And well, we're going to use another algebraic relation that I invite you to check, which is that since, remember that k can be only 0 or 1, then I can write this ck of beta in the following way. And this means if now I plug in the representation of k in terms of mu's, this becomes square root of cosine hyperbolic of beta, hyperbolic sine of beta, times e to the minus 1/2. And now you start seeing the duality a bit better. Now all we have to do is to plug this expression back into the partition function. And this is going to give us some overall factor that depends on n and beta, but not on the spins, which for now I'm not going to write down. Then we still have the sum over all the dual spins and the product over the dual links of e to the minus 1/2, so of these expressions essentially. And now all we need to do is the inverse of what we did before. So before we turned product over nearest neighbors into a product over links, and now we're going to turn a product over links into a product over nearest neighbors. And now we're done. So we have rewritten the original partition function that unfortunately I deleted, but let me write it down next to the new one, which was just a sum over all the spins times a product over nearest neighbors of e to the beta I sigma j. So we have written it as something that formally is the same, only with a different temperature. So if the temperature of my original model was beta, now the new temperature of the dual model, beta tilde, is a monotonically decreasing function of the original one. So if I just call this beta tilde, we have, and also including the minus 1/2, we have exactly the same partition function, modulo and an important factor in front. The very last step to essentially prove the statements I made at the beginning is to say that, well, if you look at the free energy, in the limit of an infinitely large system, then, well, we're going to find that the free energy of the original model is equal to this, where this is the free energy of the dual model. Let me call it star. And this factor here comes from this number that I didn't write, sorry, this function that I didn't write down explicitly. Well, the other reason why I wrote the free energy is because let's say that the original model has a critical point, so a point where this function is non-analytic. Well, then if it's only one, also the dual model has only one critical point, and they have to be the same, because there is, I mean, at this point, the hyperbolic sine is analytic, so the only things that can be non-analytic on this other side is the free energy of the dual model. And so this is kind of a quick argument as of why the critical temperature of the original one should coincide with the critical temperature of the dual one. So this is, I mean, at the quantitative level is more or less all I'm gonna do for you today. What comes next? Well, okay, there are still quantitative arguments, but a bit more general. So now we've proven our duality, and we've proven also that the point we care about, so the one where the scalar is massless, is the one that is left invariant by this duality. You might be bothered by the fact that this is not really a symmetry in the traditional sense, because we have related, exactly as in the picture we draw at the beginning, we're relating some 2D Ising model with something that is coupled to a gauge theory. And now, well, we start to understand better some of the elements of this picture. So first of all, this wall here is the duality operation that we painfully constructed. Second of all, this line here is the gauge Wilson line that we talked about before. Now I just want to give you a couple more details on how to interpret these operations as symmetries. So first of all, there are many alternative ways of constructing this duality. I've used probably the dumbest one, but there is another one which is due to Kadanov and Cheva, where they show that imagine that initially all the j's have the same sign, okay, and now construct your dual lattice. Let me maybe make it a bit bigger, because I need to draw a path. Now, yeah, draw the dual lattice, and you want to compute, say, the correlation functions between the spins in this dual lattice. What they prove in this paper, which you will find in the notes, is that if you want to compute the correlation function of two mu's, say at point R1 and R2, you can take any path connecting them and then switch the signs of the couplings in the original lattice that cross the path. Okay, so let me say that J is the configuration of the initial configuration of couplings where they are all the same for the original lattice. And now I'm gonna also have a configuration J tilde where the couplings along these links have changed sign. So in this paper, they proved that you can compute these correlation functions by taking the ratio of the partition function on this J tilde configuration over the original one. Okay, this is not trivial to see, but it's true. And they also proven that the story is path independent. So also if you choose a different way of joining the two mu's, it's still true. And also that you can generalize this construction to higher point functions. So the even ones can be constructed in a similar way, the odd ones vanish. And so another way in which people understand this line, they call it a meta line, because switching the sign of the coupling is equivalent to switching the sign of only one spin, right? And so the way they see this picture is also that you have to think about it as a line operator. And when a spin crosses it, you change its sign. And so this is maybe the first manifestation of a generalized symmetry in this story. Well, actually, secretly, also the duality is a generalized symmetry, but I haven't told you why yet. I'm telling you this just because you might encounter also this perspective in the literature. It's very hard to interpret if you don't know the whole Kardanov-Cheva construction beforehand. So yes, so this is one detail to keep in mind. One more detail, which is not crucial for us, but I want to tell you again because it's useful to understand these papers, is that you can interpret this duality as gauging the original Z2 symmetry. So here we found a gauge Z2, but it's not really the original one that you gauged, it's another one. Let's say you start with your lattice and you have an honest Z2 symmetry. So in your original theory, here you have an honest Z2 symmetry. So if you set sigma to minus sigma, everything remains invariant. So this, I'm calling it an honest Z2 symmetry because essentially is relating different correlation functions. It's telling you that these two correlation functions are secretly the same. Instead, the gauge symmetry acts trivially on all correlation functions. When you act with the gauge symmetry, nothing changes. So let's say, okay, you start with your original lattice and with this honest Z2 symmetry, and then you gauge it. So now I'm adding a gauge field, sorry, a gauge Wilson line, also for the original symmetry. My claim is that this model is equivalent to this one. And the way you can see it is by this construction, because switching the signs of the links along the path is the same as making a gauge choice so that the taus along the path, so let me call gamma the path, are -1, and all the other taus are +1.
Sorry, what is tau?
Tau is the same as U, so it's a Wilson line of the Z2, but for the Z2 of the original model. Yeah, and so essentially, since computing the correlation functions of these mu's corresponds to choosing different signs for the couplings along the links, you can also phrase it as gauging the initial Z2 symmetry and making a certain specific gauge choice for the gauge fields. And again, this is not crucial for us, but it's useful to interpret the papers if you ever feel like reading them. What instead it is interesting for us is that, as this picture suggests, you can interpret also the duality itself as some sort of generalized symmetry. It's what people would call a categorical symmetry or a fusion category symmetry. This means something much simpler than the name suggests. So let's say that you have some group elements A and B. Usually, well, the product of two group elements is just another group element. Instead, in this kind of symmetries, it's a linear combination of multiple group elements. In particular, this means that sometimes you don't find the inverse of an operator. You might have that, say, GA dagger gives you, again, some sum. And this is the case for this duality. So let me call eta the line operators that implement this Z2, so the original one. By implement this Z2, I mean that if you have a spin and you move through this line, it becomes minus itself. This is again, well, this is in some sense the mother of all definitions of these generalized symmetries. So the understanding that brought to all these works on generalized symmetry is that you can think of a global symmetry as an operation that acts on all of space simultaneously, but you also can think of it as a local operation because it acts on local objects. So you can construct extended objects, let me call them surface operators or line operators, or sometimes they call them topological defects operators that act locally. So when you move a charged object through them, they essentially act with a symmetry operation on this object. this is just a definition, okay? It's just a definition of these extended objects. You call them topological defects because they don't depend very strongly on the surface on which you define them. So clearly, if you drew this line this way, it wouldn't change anything, or if you deformed it in some weird way, provided that you don't cross charged objects. And defects probably because when they act on local operators, they have well a dimension less than the space-time. So, but okay, maybe I mean I don't wanna. I mean this is my interpretation of the name. All right, so maybe let me finish the story about the duality, and then if you want, I can tell you a bit more about how to use these local operators. So I call eta the line that switches the sign of the spins, and then let me call n the line that implements the duality. So if you move sigma to n, it becomes a mu attached to this gauge link that also implements this sign switch of the spin. Then, well, I can try to construct the algebra or the generalization of the algebra. So something like this for this categorical symmetry, which are usually called fusion rules. So clearly, if I apply two etas, well, I just get the identity. So this is trivial to see. If I apply eta and then n, I just get n. This is also trivial to see because eta leaves the whole theory on this side invariant. So I can first apply eta. Nothing happens to my partition function. Now forget that I gauged it. Then I apply n, and I have the duality. Similarly, if I apply the duality and then eta, also you still just get the duality. So the only remaining question is, what do I get if I apply the duality twice? And the answer is this. And I have an heuristic argument for you, but I have to say that even I am not fully convinced by my explanation. But my heuristic argument is the following, is that the duality doesn't keep track of the overall signs of the spin sigmas. So if you phrase it in terms of switching the links along a path, as we did before, it doesn't care if all the j's outside the path are negative and then all the j's on the path are positive, or vice versa. So essentially, if I change sign to the spin sigma, to an odd number of the spin sigma on this side, the duality deletes this information. It doesn't know about overall signs. And so when I apply it twice, so first I apply it once and I get my mu's, but then the mu's don't know anymore if they come from a theory where, let's say, okay, let me just do it with 4. Okay, so the mu's don't know anymore if they come from a theory that looks like this, or if they come from a theory that looks like this. So we call this sign switched. And so in principle, when I apply the duality twice, I get a linear combination of the two possible theories that generated the same dual model. And this is why, okay, people would tell you that this duality operation can be thought of as this categorical symmetry, or in language closer to particle physics, as a non-invertible symmetry. Of course, you have to keep in mind that it's not really an exact duality when you're away from the critical point, because this Z2 symmetry is gauged on the other side. So it's not exactly the same theory, but they are very close, because as I told you, locally gauging the symmetry doesn't do anything. Okay, there were a lot of details. Now let's try to make a connection to the hierarchy problem.
Before you go, I have a point when you talk about the facts.
Yes.
The facts, you mean that when you integrate the formula before, what are your paths? Because you did something like the paths we define when the analytic functions, Green functions theory, have some similarities. So you said that when you draw the two paths there. Yes, you draw
for the operators.
Yes. Say I can take also another one to avoid something. What do you mean? That you
No.
have equivalence.
Yeah, so these operators, so these operators are defined in the following way. So let's say that let me do it properly, okay? So let's say that I have some continuous symmetry, some U1 or whatever you like, associated to some, and this symmetry has some current, okay? Then, I can define a one form from this current, and then I can define the dual of this one form. And for those like me that don't think about this kind of notation all the time, let me say it explicit, okay? For you that asked the question is trivial, but let me say why I did that. So I did that because the charge of the symmetry can be written as, let's say that I'm in d dimensions. You can write it like this. Okay, and the dual of a P form, so a P form is just P differentials that are contracted antisymmetrically. The dual of this P form in d dimensions is this. So essentially, it's turning the P form into a D minus P form. I'll show you in a second how. So this is an antisymmetric tensor with D indices, a fully antisymmetric tensor with these indices. These are metric tensors with indices going from 1 to P, so the original P, and then there are differentials that go from P plus 1 to D. So this is the star operation. And so if I apply the star operation to my original current, I have a very compact way of writing the charge. So the charge is just the integral of this J over all of space. You can check this using the definition. And J contains in its value already the differentials. So that's what makes the notation convenient. And so how do I define one of these surface operators that implement the symmetry? So let me say that it's really some U1 in ordinary 4 dimensions. Then I would construct an operator that's associated to some 3-dimensional object in space-time. Let's say a sphere. Okay, let's say I have a sphere sigma. And some parameter of the transformation. And this object is just this. And then if I put a charge inside, a charge local operator with charge Q, the action of this U is very simple. It's just a symmetry transformation times applied to the operator. This is some modern way of thinking about symmetries. And this eta, for me, was the same for the Z2. So essentially, in this, so here we're in 4 dimensions, and I was defining it over a sphere. Here I'm defining eta over a line, and if a local object crosses it, I act on it with the Z2. Okay. Why did I say that it was topological, so that it didn't matter if I deformed the line? Well, it's easier to see, at least for me, in this example. So let's say that I deform the surface sigma. Then my u of sigma prime, it's gonna just be e to the I alpha sigma minus sigma prime integral of j times the original one. And now let me say that, so this is sigma prime, okay? So the difference between the two doesn't contain any charged operators. Then I can just use Stokes' theorem to first write this as the integral over this boundary. Well, this is really just, I'm just calling sigma minus sigma prime the boundary of a region. And then now I can use Stokes' theorem to say that this is equal to the derivative over the region. And since this is a conserved current, inside of M there are no charged operators, the conservation of the current in this language is just this. So this becomes 1, and these two operators are the same. And so it's not completely true that they're topological, because if you put a charged object and you deform the surface, there is a difference. But people call them topological for this reason, because they're almost topological. If you deform a bit the surface, nothing bad happens.
Sorry, just to be clear, when you say the action of U sigma alpha on the local operator OX, you mean making the U or U dagger or something like that? What's the action of U?
Yes, it's this. So essentially, well, I mean, geometrically, you can think of, let's say, squeeze the surface, so or like make the operator pass through, and then I want to define the action of U as the C. So U. So this is, if this was a U1 symmetry, you would say that the local transformation of O is this, right? So Q is the charge under the U1 symmetry. Alpha is the parameter of the transformation. So this is just an element. So this is just an element of your U1 symmetry. I don't know if,
I don't understand, but if you are, say, in a Hilbert space where this
yes,
operator lives, then I have an operator U which acts really as a similarity transform on O and gives you the.
Well, that would be the normal story of the symmetry.
I don't have an Hilbert space, and U is just a way to construct an element of the group, you are saying.
Yeah, so U is just a purely local object that acts on purely local objects. So it's, I mean, the easiest way for me to see it is that it's acting on local operators. If you want to think of it as acting on the states of the Hilbert space, well.
No, I want to say, let me say, you have a correlator. You have
yes.
OX, OY bracketed.
Yes.
And then where is U here? How do I insert U to act on this? That's what I don't understand.
Yeah, I see. Well, so yeah, so this well, so essentially you can insert it in different ways. So you have to think of it. So you have to say, you have to decide the surface sigma, and then see which ones of the operators in the quadrator are inside and which ones are outside. So let's say that
one is outside, the other inside.
Exactly. Then this thing would act on the correlator in the same way. Let's say that this is a symmetry, so they're the same under the action of the operator. Then this would give me e to the I. Well, let me call, let's say, 1a and 1b, so it's even clearer. Okay? So a is inside, and it has charge QA, and B is outside, and it has charge QB. Then the action is e to the I, well, alpha is, again, the parameter of the transformation of your choice, QA, A of N, B of Y. If the, let's say, in the opposite case, the action would be e to the I alpha QB. If both were inside, you would have e to the I alpha QA plus QB. And the statement that you have asymmetry of the theory is that all these operations give you the same correlation function. I forgot now what, yes, what I wanted to do. Well, I think this is a good time to take a break because we made a big digression on this generalized symmetries. But what I want to do next, which is not going to take an hour, is just, well, now we kind of have an understanding of this duality, both in the traditional sense and in this more modern sense. And I want to see what it can do for us in the continuum. And as I told you, I don't have a definitive answer yet, but I will give you some ideas of why this operation can be interesting in the sense of protecting the mass of a scalar, at least in 2 dimensions. But before breaking, let me say, so that if someone wants to leave, they can, that there is, at least as far as I know, there is no way to generalize this to higher dimensions. Because if I take the same story in higher dimensions and I gauge the Z2, I'm not going to get something that is almost the same as the initial model. I'm going to get just a duality between 2 different models. And well, so there is no way of interpreting this operation as a symmetry that could protect a mass parameter. So this is, I mean, you already sat with me for an hour, so I should have made this disclaimer at the beginning, probably.
Or maybe not.
Or maybe not. But the whole point is that this is inspiration for what might or might not be happening in 4D, but it's definitely not something that you can translate precisely to our problem. But as I said, okay, this was in the spirit of the bonus lecture, so we are having fun. All right, so let's, well, if you have questions, I'm happy to answer. If not, take a break.
More questions? Online, hi. So.
Over the break, I was answering questions. I think it's important to report also for the online viewers, which is that, okay, we talked about this duality as something acting on the whole lattice. So it might be confusing when I write n equals 1 plus eta. But what I mean is that you can interpret also the duality as a local operation. So let's say you draw, again, a path through your lattice, and this is an n line, and then all the spins that cross it get switched to mu spins. Okay, so on this side of the line, I have my original lattice. On this other side, I have my dual lattice. If I really want to be precise, I can attach lines to the mu spins to keep track of gauge invariance. What this relation means is that if I put 2 n lines on top of each other, then these are equivalent to an identity plus an eta line in the same position in the lattice. Okay, so it's kind of, I mean, it looks a lot like an operator product expansion in CFT, and indeed there are some analogies. All right, having done, yes.
This is the same thing I ask you. I don't understand. Because before you wrote another line and you said something that it is equivalent to say that this path, the new path that you wrote, it means that you can avoid the passages from one to another, something like singularity.
Well, so yeah, I mean, in some sense,
I could. There is no now you can. Yes, it was my question, but it doesn't matter. For the moment, I understand. But when you said something about another path.
Yeah, so
To avoid, what do you would avoid?
no, I didn't want to avoid anything.
Oh,
I just meant that if I draw another path that doesn't cross any local operator, I mean, in addition to the ones crossed by the original ones, the two paths give me the same
You say,
action
okay,
of the
without crossing
Yes.
the passage, I mean, the singularity in some sense.
Yeah, exactly. So if you don't cross the charged objects,
Yes.
I mean, if I cross the same number of charged objects with two paths, the two paths give me the same action of the
Okay,
scene.
something, yes, nothing sound.
Yeah, so let me make a couple of comments on the continuum, and then in principle for today we can be done. I was also potentially planning to talk about something that a few people have asked me, so how to go from the coupling of a scalar to GG dual, so the strength to the potential that we've used many times before, which is complete. If you write down correlation functions between spins, let me write them in a way that reminds us of the continuum, where this tau is just some integer number times the lattice spacing. So let's say that my lattice spacing is A and L is an integer. I can suggestively write down correlation functions as b to the minus tau over some correlation distance. And as we approach the critical point, this correlation distance diverges. And so we can think of integrating out high energy, short distance degrees of freedom to get some smooth description of the system that, at least in a neighborhood of the critical point, is equivalent to our discrete model. And the way in practice in which one does it is by averaging spin variables over some region of space. Where this region of space will depend on the correlation length, so it's maybe roughly of order of the correlation length squared, and is centered at this point on the left-hand side. So I want to define some field variables phi, which are just the average over some region of space, so my original discrete variable sigma. The first thing to notice, which is useful for us, is that this phi, I mean, even if the sigmas were taking on discrete values plus or minus 1, the phi's take on real values. You just can see it from the averaging procedure.
What do you take for H? H
is just the original Hamiltonian. So this is just an average. So it's just this object. That's what you would call the correlation function of one spin in your original theory. So this A, I mean, let me write it. Why not? So my H is what I had from the beginning. So the sum over nearest neighbors of.
No, it's okay. I was confused by the fact that you use H sigma I and sigma I in the sum.
Yes, you're right. Yes, I should just call it H. All right, so I'm not going to be very precise. I'm just going to give you an heuristic derivation and some arguments. So what does the theory for these phi's look like? So first of all, let me take a continuum limit of the Hamiltonian. So I can conveniently write the Hamiltonian in this way. I mean, I'm just completing the square and then subtracting off the 4 sigma squared from the nearest neighbors. I'm not neglecting this term because it's true that at this level, now that we are still on our lattice, this is equal to 1, but in the continuum, it will map to some real value function of phi squared, phi to the 4th, etc., etc. Now we can take the continuum limit of this object. The easiest way is if we multiply by lattice spacing squared, divide by lattice spacing squared, and take the limit of lattice spacing going to 0. Then even by I, you can see that this goes to something that looks a lot like an Hamiltonian that we're used to in quantum field theory.
Phi instead of
So this, I think. Yeah, sorry.
phi or x, no?
No, that's the point actually. So
Sorry.
this is just the continuum limit of sigma. Okay, so if my lattice spacing go to 0, so this is what these variables look like if the lattice spacing goes to 0. Okay, so here I might have made yeah, so this is fine. Here I have a j to match, I think, and here I have a 1/2 that should go here. All right, so now makes more sense. Okay, now the point is precisely that sigma and phi are not the same object, because phi is an average with this factor in. And so in reality, sigma is some complicated nonlinear function of phi. Okay. Maybe if I do a mean field theory approximation, I can even compute what complicated nonlinear function this sigma x is of phi x. So let me just write everything properly. Okay. Maybe I can even do it, okay, but I don't really need to do it. I can just expand sigma as a function of phi in the lowest order terms that allow me to describe the phase transition and are consistent with the symmetries of the theory. So in practice, I can just plug this unknown function of phi back in my continuum Hamiltonian, expand the sigma squared term, and I'm gonna get some effective Hamiltonian for phi that looks like this. And I rescale the kinetic term, so I've canonically normalized phi by dividing by square root of j, and then I'm defining some effective couplings m squared and lambda, which in principle, if I wanted to, I could try to compute from the microscopic theory, but for my purposes, I don't need to do it, so I can just match them to the phase transition. And in particular, what I care about is the mass. So as we said, when the temperature goes to critical temperature, these correlation functions show like long distance correlations. And so, well, for the scalar, the correlation functions also would look like this. And so if I want a phi theory that reproduces my phase transition, I want some mass squared that goes to 0 at the critical temperature. Now,
because you have defined the phi in terms of the discretance. Yes, it is a correlation function, you say.
Yeah, the
phi, yes, with some Hamiltonian. Okay, so you do the meaning, and after that you inverse and you say in the continuum limit, you define the sigma when the distance becomes 0. Yes, you take.
Yeah, so this is not an average. It's really the spin in one point.
This is not the same sigma that you have in the definition of phi. And how do you inverse?
No, in some sense it is, but it's on a lattice that is dense.
Yes. So you take the continuum. You take the continuum, yes?
Yes.
So Our universe, and you say sigma of phi.
Yes, so in principle, I would have to compute it from here, what sigma of phi is. So it's a complicated nonlinear function, but I don't want to do the calculation
Okay.
because
Okay.
all I need is an
The
effective
inverse.
theory of phi.
But you suppose the universe.
Yeah, supposedly that's what I do.
That's you have
Yes.
meaning. Okay.
Yeah.
On the second, on the last line, so on
But let me just add one small thing. This is not a real derivation, okay? It's just an heuristic way of showing you why this phi square phi to the fourth theory is a good description of my original lattice model near the critical point. Yeah.
Actually,
Oh, sorry. What part did you-
so, when you go from the two lines on sigma, between the gradient squared and the 4 sigma squared,
Yeah.
they keep the numbers keep exactly like this. In the gradient squared, there shouldn't be a delta x squared privata or something like that.
Well, what do you mean here?
Yeah.
So here, what I'm doing is, so remember this is a sum over nearest neighbors, right?
Yeah.
So I can write it is, so let's say that now the split in between nearest neighbors is becoming very small. Let me call it delta x. So I can write sigma I, say a sigma of x minus sigma of x plus delta x. Okay, then, so this is two-dimensional. Then I divide by delta x and I multiply by delta x. Okay, so this vector means that this is delta x times delta y, really. Okay. And so what do I have? So I have this squared, so times, let me call it delta x delta y, okay, just to be fully explicit. If you want, I can call this, well, let me really do it completely, okay? So I have this, no, I don't want to delete this. Sorry. Let me delete, let me do it upstairs. So I have sigma I, sigma j squared, and I'm writing this as sigma of x minus sigma of x plus delta x over delta x times sigma of x minus sigma of x plus delta y. And this is just to say that I'm doing it the two directions times delta x delta y. I just multiplied and divided. And now take the limit of delta x and delta y going to 0. Well, sorry, you can do it more. Let's really do it properly with the vector science. And then this is gonna give you, so these two are gradients. Yeah. This is gradient of sigma, this is gradient of sigma, and this is the integral. Let's see. When you take the limit of delta x going to 0 here and also here. Yeah, so going back to the continuum, so to the phi theory. So in this phi theory, honestly, I'm not really sure if the duality carries on or not. Very naively, but I'm not sure that it's true, I would say the following. Well, let's say that this phi theory describes my sigmas, okay, my sigmas near the critical point. then what stops me from defining a phi mu theory, where the mass is minus that in the phi theory, which describes instead the mu correlation functions near the critical point. Very naively, this would reproduce the correct physics, at least as far as the phase transition goes, because as we said before, the mu's at high temperatures give you the correlation. Let me write it explicitly. So the correlation functions of the mu's evaluated at this temperature give me the correlation functions of the sigmas evaluated at beta. So when you are at high temperature on the sigma side, you're at low temperature on the mu side, and vice versa. So when on one side all the spins are pointing in the same direction, on the other side they're all disordered and messed up, and vice versa. And so this phi theory essentially is describing the approach to the phase transition from the sigma side, where you start at high temperature on the sigma side, and you're going to low temperature. But if I invert the sign of the mass, I'm describing the opposite approach to the phase transition. So I mean, this is my very naive take on what might be going on. Of course, this is ignoring the subtlety about the gauging that I told you before. But there are many equivalent ways of thinking about the discrete gauge symmetry, some of which are topological quantum field theories where you have some non-propagating degrees of freedom. So maybe the phi nu theory has to be coupled to one of these topological quantum field theories without propagating degrees of freedom, and then the duality is complete. Honestly, I don't know if this very naive picture is right or wrong. There is an argument in a paper by Seiberg that it's in the notes that tells that instead the Majorana fermion continuum description of the model does not have the duality. So maybe we're being too naive by making these identifications. And well, this is all I have to say about this story. So to me, it's very intriguing because I would never, ever be able to get this symmetry or duality or whatever you want to call it by looking at the Lagrangian of the continuum or by looking at the Hamiltonian of the discrete model, but it exists. And intriguingly, it protects in some sense the critical point. So the only point that is left invariant is precisely the point where the scalar mass is 0. So this, rather than a lecture, was more of a collection of thoughts that I'm having, and I hope they inspire you. So we could stop here, or we could have an appendix of the course where I show explicitly how to go from here to here, which we used many times. But I never computed, where f is a periodic function. So this has nothing to do with what we've talked about so far.
How long does it take?
It's in the appendix of the notes, and many of you asked me. Okay, I see that well, how much time do I?
50 minutes.
50? Okay, but
It's correct, that one.
Yes.
At most, I mean, it's uppercut.
No, I think it can take much less than that. Well, much less, maybe it's an optimistic statement.
5 minutes, it's okay.
5 minutes.
Much less, it's an order of magnitude less. So.
No, it's not an order of magnitude. Well, depending on how many details you want, I can do it probably. So the fastest way it's 15 minutes, 20 minutes. The longest way, I can take up almost all of it. But yeah, yes. Who wants to go first?
Yeah, maybe like so if you do because when you try to argue for the continuum limit, you started from the discrete and then you build up the theory and made some continuum constraint.
Yes.
But in principle, you could imagine that you do it exactly. Exactly. I mean that I start from the discrete and I always have a discrete thing, but I start to write fields that are picked on values. And then you start to say, okay, now can I do some like functional version of can I once I have the Lagrangian that is a field theory Lagrangian, but
Yes.
that you know that there's always a discrete structure inside. Then I know that the discrete structure inside induces a symmetry, induces the exact symmetry. So in principle, I should be able to track this symmetry in the functional form of the. So I don't know if this is clear or not.
Yeah, no, I see what you're saying, but I mean, I would say that the closest to what you're saying is this thing that I
This
just
is
said.
the first order in the mass term, but in principle, if you really do the discrete thing, you have all the terms, right? You have all irrelevant terms, and then this symmetry induces some structure on these irrelevant terms that is left, that is changed in some way. So in principle, this is exact because I'm not doing anything. I'm just rewriting a discrete model in a field theory, but that is always discrete.
I mean, technically, that's what I wanted to do in some sense, because I mean, the fact that there is a precise, I mean, the model is still discrete, but if I don't have enough resolution to see distances of order c, this description is the same. I mean, I don't know, I have the impression that we're saying almost the same thing, but you just want to take it a step beyond. So that instead of just showing the simple relations to the mass, you want to really compute lambda and the coefficients of the relevant operators in a Wilsonian way, let's say, by integrating out the energy degrees of freedom, and really see that if you do it on both sides, on the sigma and the mu side, then I have a precise correspondence between the parameters of the two theories. I think you can do it, and actually that's what secretly I've done here for the mass, because
but this is, to me, I mean, if you do 3D, what goes wrong with I mean, this is just, I mean, this is generic, right? I'm saying, you're saying, okay, if I have a negative mass, I go on one side.
Well, I think that in 3D, oh, maybe you can correct me if I'm wrong, but I think that in 3D, the muse, I mean, like the theory that described by the muse is not anymore the same as the theory described by the sigmas. So if I integrate out the muse, I'm not gonna get the exact same.
Yes, but here, where do I see this in the field theory that you wrote? I mean, the fact that
No, but here I'm still in 2D, where if I integrate out the sigmas, I get this field theory. If I integrate out the muse, I also get this field theory, but with different m and lambda. I'm afraid that in 3D, if you integrate out the sigmas and the muse, you don't get the same field theory on the two sides. That's what I think it's going wrong.
But close to the critical point, I mean,
yeah, close to the point, these are effective descriptions that should always work.
Exactly. So where do you know that close to the critical point, there you are in 2D and not in 3D? So it should be in some irrelevant terms that you have thrown away somehow. I don't know. I don't see if you see it.
Yeah. Yeah, I'm not sure. Yes, I'm not sure how to answer the question. Also because, as I told you at the beginning, I wasn't sure I could answer all your questions because, for example, another thing that I don't understand in all its details is the precise proof that if you start in this, let's say you start this in 3D, and then you gauge its Z2 symmetry, you're not gonna get another Ising model on the other side. So that's also the part that I don't understand constructively well enough for you on the blackboard. And for the same reason, I'm not exactly sure how to answer your question, because I mean it's true. This is an effective theory that describes anything. I mean, you change the dimension here, and you're happy.
Yeah, but the very notion of irrelevant depends on the dimensions. In 2-dimension, phi is massless.
It's dimension, yes.
Dimensionless.
Yeah,
and so the irrelevant actually you stop to phi force in 2 dimensions, but why?
It's up to type just because this is enough to describe the phase I mean, like the part of the phase transition that I care about. Indeed, I mean, okay, there is also, I think, some sense that close to the critical point. I mean, let me tell you why. Because even if it's dimensionless, close to the critical point, the value of phi is proportional to the mass, and so it's small. And so higher powers of phi are smaller than lower powers of phi.
And also, I wanted to say that you wrote that the mass is linear in the temperature.
Yeah, this is an expansion.
Yeah, because okay, that's a Taylor expansion, something like that.
Yeah, and at these, yeah, so I'm close to the critical point, so I'm expanding in small differences, and in this limit, the relation between the two betas is really this. So one is minus the other. So all right. So, but I think we should think more about what you asked offline, because if it works, this is exactly why I started thinking about this, especially if it works in 4D, not in 3D. But maybe 3D is already enough, because I can always think of time as the temperature. So already 3D, I think, would make us happy. So I think you had another question.
Yeah, there's something basic. I'm not sure I understand. If you have I vaguely understand that if you have a symmetry, you can say, okay, this parameter, like the mass or whatever, can be protected, and if the symmetry were exact, it would be 0, etc. Here, from what I understand, you have a mapping between one sigma model to one mu model, and with the correspondence between the two betas or the two differentials between the two models, and at the critical temperature, somehow the correlation.
But wait, the important point is that the sigma model and the new model are the same model locally.
Yes,
Okay,
yes.
the only difference between the two models is that the Z2 symmetry that was a global symmetry on the sigma side is a gauge symmetry on the new side.
Yeah.
But since locally you can always make the gauge choice that the gauge Wilson lines are one, you would not be able to see it locally, that the two models are different. So it's true that if you want to be precise, this is not really a symmetry transformation. But locally it acts like one, so it's sending the 2D Ising model into itself. That's why it's interesting for me.
Yes, but my question is, and then at the critical temperature, the correlation length is infinite, and the mass, okay, goes to 0. So my question is, why, in practice, should you be at the critical temperature?
Why should you be? In what sense? No, so this is just an effective description that is valid not too far from the critical temperature. So that's the part that should make us feel uneasy about possibly solving the problem with this symmetry. Because already the description in terms of the scalar that we care about is only valid if you're not too far from the point where the mass is 0. So clearly using this whole story to explain the hierarchy between the mass and in this case the lattice spacing, which is so the inverse lattice spacing, which is the UV cutoff, it's not so obvious because this effective description really works only when you're already close to the critical point. So this is another of those questions that I don't know.
You mean, I mean, going from the discrete to the continuum, works only when you are close to the critical point. But
well, it does. I mean, the continuum describes the same theory as the discrete close to the critical point.
yeah, but even if we don't care about that, I mean, if we just look at the discrete already, I mean, I mean, this theory is valid whatever temperature you are.
What theory? The phi theory. Or,
Yeah,
or
or
the,
the
no, sorry, the
the
discrete
discrete one.
Yes.
But what special? I mean, why should you be at the critical beta?
I mean, yeah, I mean, there is no, I mean, it's the same as asking why a fermion mass is zero. Okay, it can be zero or it can be something else, but the point where it's zero is stable under asymmetry. That's all we're saying. I mean, I don't know if the answer, I mean, the answer was a bit terse, but it was also precise in the sense that you can ask the same for SUSY breaking, okay? SUSY break, so let's say you want to explain the X mass via supersymmetry. There is no reason why the SUSY breaking scale should be the X mass that we observe. It could be the Planck scale, it could be the GAT scale, it could be much smaller. The only thing that's relevant to solving the problem, though, is that if you measure the X mass and then the SUSY breaking scale on top of it, you would have no stability problem for the hierarchy. So the hierarchy between the SUSY breaking scale and then Planck is stable. So if you find the X mass and then all sorts of superpartners around it, you're not surprised. I mean, that's how you think nature should behave. But if you do a dimensional analysis estimate of the X mass, this should be the SUSY breaking scale roughly. Okay, there can be factors, loops, loop factors, etc., etc. And then your question is, why is the SUSY breaking scale not M Planck? Well, that's something that you should ask God. But I can tell you that this choice is perfectly natural. It's technically natural because this scale is breaking supersymmetry while this scale doesn't need to break supersymmetry. And so when you do all the exercises that we done in the first lecture of the selection rules of the symmetry, blah, 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 when you ask what's the natural value of M SUSY, well, it's whatever it wants to be. It can be anything, okay? Because you can put on this side of the squiggle only other scales that break supersymmetry. And if M Planck squared doesn't, it has no way to appear on this side. You see, I mean, does that answer?
So you say you are playing the same game here with beta.
Yeah, I mean, the only okay, the main difference here, yes, kind of. If this whole story carries through in the way that we hope it does, okay, but let's say that you could show that this duality in the continuum, it's really a symmetry and it's really protecting m equals 0, then if you were to find m equals 0, you wouldn't be surprised. And even if you would find m a little bit different from 0, you would not be surprised if you found a way of breaking this symmetry a little bit. See? But no, it's a very good question. Actually, many people ask it to me, not in these cases, but in the multiverse cases, where you fix the Wick scale from, say, the mass of some light other scalar like the relax. There, the answer is the same as well. So the mass of that other light scalar could have been anything, but when you measure the X mass, you're fixing it in some sense. So it's a way of explaining why an apparent big hierarchy between the X mass and then Planck instead is natural. Of course, the hierarchy would have been different by orders of magnitude. Nature would not have cared if it was different. Maybe we would not have existed, but whatever. But it would still have been a technically natural hierarchy, so a hierarchy that doesn't bother a physicist that looks at the symmetry of the model. Yeah. Other questions? Maybe, I mean, I think we've I mean, I don't want to go on another half an hour on a completely disconnected topic unless you guys insist. I think this is a good time to stop. I mean, clearly the story was intricate and poorly understood by me enough that it generated a lot of questions. And so, I mean, it feels like a good time to wrap it up on these more speculative notes of this possible symmetry, rather than spending another half an hour on technical details that you can find in the notes. Well, I mean, okay, maybe calling them technical details is unfair, because there is a lot of interesting physics going into this. But I mean, I don't know. It feels unfair to you, the audience, to now switch completely and have no continuity whatsoever after all this work that we did on this other subject. If you agree with stopping here, maybe I will add only one tiny comment about what I said last time on UV-IR mixing, and then wrap up with some philosophical conclusion. Or do you want to see this? If you don't say anything, I'd say I'll take it as a no for saying this instead of a yes. Usually, silence means yes.
I have a master thesis too.
Ah, all right. So that sounds like a no to me. So
See you later.
see you later.
Thank you very much.
All right. So let me just make one comment on the UVR mixing story that we talked about last time, and then wrap up. So if you remember, last time we had this non-commutative space-time, and then we were seeing that some pole was generated at this scale, where lambda theta is the eigenvalue of this matrix. Let's say all the eigenvalues are roughly of the same order, lambda theta. So the inverse of this lambda. So this lambda is an energy scale, so the inverse is the eigenvalue of this matrix. And m, little m squared, was the mass of the original scalar in our theory. And then, if I remember correctly, I said that, okay, I wouldn't call this true UV-IR magic, because if you take little m to m Planck, or the UV cutoff, which is its natural value, if you take lambda theta to the same UV cutoff, then, okay, there is also a loop factor here. Then you get for the mass of this new pole exactly what you would expect. So a coupling squared over a loop factor times a Planck squared, or the cutoff squared. However, well, I think this was a bit unfair, because to this idea there is a little bit of UV-IR magic, because let's say that now I do take m squared all the way to the cutoff. Okay, so now this becomes say, well, MUV squared. Now lambda theta can be anything, because it's a scale that's breaking the Lorentz symmetry. And so if I take it at any intermediate scale between us and then Planck or MUV, not all the way to MUV, then this pole is at a much smaller value than I would naively guess using just the symmetry. So there is an interesting UV-IR effect going on. On the other hand, I don't take back the core of what I said last time, which I think that the important part of this mechanism is still that you're breaking a symmetry somewhere, because if there wasn't this lambda theta scale that is stable, I'm not sure that you could stabilize an IR pole just by mixing high and low energies. However, well, I'm not sure. So I'm not aware of anyone who has tried to do something similar without breaking the Lorentz symmetry. This is some other food for thought. So after this small comment, which is not so small, but it's short time-wise, well, let me just wrap up. So well, we've seen a plethora of ideas that that can explain why the X mass and the cosmological constant are much smaller than we expect based on symmetry. If you have to take only one message from these lectures, well, you should take two, really, not only one. The first one is that the problem of explaining the X mass and the cosmological constant can really be phrased as a failure of symmetry. So you use symmetry to estimate the value that you expect for them, and it's orders of magnitude off compared to expect. So it has nothing to do with radiative corrections, how you regulate loops, etc., etc. So whenever you find a paper that claims that we don't know how to compute loops and that explains these two parameters, you should already be suspicious. The second message that I think should emerge from this series of lectures is that no matter what was your favorite explanation in the long list we gave, no matter how crazy you consider some of them or how realistic some others, the answer will always be extremely interesting. So the most conservative answer we can give implies the existence of a new symmetry of nature, a new fundamental symmetry of nature, other supersymmetry or scale invariants. The most adventurous explanations that we can give are those that we've seen today and last time with UV-IR mixing, and even break. Well, today it's actually more of a symmetric type of idea. It's just a bit exotic. But those that we've seen last time with UV-IR mixing really break completely quantum field theory, and our intuition is turned upside down. And in the spectrum, going from the most conservative to the most radical, the middle is equally interesting. So the multiverse of the landscape also offers a completely different perspective on nature that forces you to think about other questions in a different way. So if these parameters are telling you that you live in this vast multiverse with many different vacua, well, then also other model building questions, other questions about the fundamental laws of nature take a completely different, have to be considered under a completely different perspective. So again, to conclude, the two take-home messages are, if you want me to fuse them into one, that these problems really concern some fundamental aspect of nature. So there is no going around this. And if you don't believe me when I tell you that it's a failure of symmetry, well, you can just constructively convince yourself of this fact by looking at what kind of explanations we'll come up with. They're all different from each other, but they all change completely the way we think about fundamental interactions. So I hope you enjoyed everything from the most conservative to the craziest option, and well, I'm happy to take any final questions if you have.
Final questions?
Which one of the expression you prefer?
Well, let's see. It's not actually. It's a good question in the sense that, yeah. So okay, the explanations that look best theoretically are obviously those based on symmetry for the X mass, by far. Okay. However, the cosmological constant doesn't make me sleep at night. So if really symmetry is explaining the X mass, why is it 60 orders of magnitude off minimum for the cosmological constant? Does it mean that, so this could mean that you have understood nothing, that instead symmetry has nothing to do also with the X mass, which is the reason why multiverse/landscape are my second favorite, but it's really hard to tell for me whether, who's really number 1 and 2 in this list. If I just look purely at the models, of course, the one based on symmetry are much simpler to write down, much more natural. But then, if I look at experiment, nature is kind of giving us a big middle finger already for the cosmological constant. So what prevents it to do the same for the X mass? So the answer is this. And then more pragmatically, if you ask me what I work on. I mean, I do not work on the symmetry ones at the moment just because they've been, in some sense, overexploited. So most interesting things that could have been said have been said. And also, they have no guarantee of giving, even if they're correct, they have no guarantee of giving us a signal within our professional lifetimes. I mean, you could say that your prior is always to minimize fine-tuning. So if you don't find the symmetry at the X mass, you should find it at 1 plus epsilon times the X mass, okay? If you don't find it at 1 plus epsilon, you should find it at 1 plus 2 epsilon, and so on, okay? However, the moment you cross this line, you don't know where to stop. And we crossed this line already at the few percent level. So the tuning you need to explain the X mass is for a few percent. So why not a part in 10 to the 4? It's still much, much smaller than what you would have if you brought the scale all the way to n black. Why not a part in 10 to the 5? And a part in 10 to the 4 is something that presumably we will be able to see if we build the next collider. A part in 10 to the 5 is for sure beyond my retirement. So yeah, so this is, well, maybe I didn't want to conclude on this depressing note. Yeah, maybe what I should add is that instead, thinking about, I don't know, multiverse plus landscape, even though I mean, there are some theoretical aspects that are less satisfactory than the symmetry ones, however, on the one hand, it allows you to really break new ground, so have new ideas that are qualitatively different from what existed before. And secondly, one thing that I emphasized last time is that it's much more detectable than you would think. So there is not only new ground to break theoretically, but also experimentally, and it's something we can do before we retire. So we cannot really exclude completely these ideas experimentally, but we can certainly confirm them if they exist. Some of them at least can confirm them. And they have some signatures that are very special, and they will tell you that's it. And if that was the case, it would be very exciting. Yes.
I'm maybe starting to realize that maybe I missed the main point of your lecture. Because you kind of suggested in your reply that there is a connection between the X mass and the cosmological constant. But couldn't it be that the two solutions, there are solutions to this problem, could be completely unrelated? That the solution of the cosmological constant could be completely unrelated to what happens to the X mass, no?
Yeah, absolutely. Yeah, no. Okay, when you started by saying that you didn't get the main message, I was worried because I mean you came to every lecture, asked great questions, so I thought, okay, if you didn't get the point, no one understood anything. No, but I never wanted to say that the two are necessarily related. Okay. What I want to say is that when you ask me, so the explanations for the two could be completely unrelated. It's entirely possible. However, I mean, when you ask yourself, what should I work on? Then you try to consider everything that nature has told you so far. And so far, nature has told you the cosmological constant very likely doesn't have a simple symmetry explanation. Okay. Maybe there is some weird, I mean, there is like this paper by Witten that suggests that maybe we secretly live in 3 dimensions because there the masses of scalars and fermions in the same supersymmetric multiplet can be split, even if supersymmetry is exact. And then there is some weird 3-dimensional supersymmetry explaining the cosmological constant. So maybe something like that is going on, although no one can write an actual model. But if that's not the case, the value of the cosmological constant, which I remind you is 0.1 MeV, is much, much smaller than energy scales that we probed to death with high precision even. And we have found no symmetry that explains it. So why would nature want to leave the cosmological constant like this, that looks like a huge fine-tuning, and then solve the X mass right on top of it because of symmetry? That's something that doesn't make me sleep at night. Now, do I want to say that this means that necessarily they are correlated? No. Also because the cosmological constant is one example, but then there are many other examples instead where symmetry came to the rescue right at the correct scale. And I gave them to you like in the second lecture in the KK bar mixing, so mass difference, the pion, the neutral charge pion mass difference, the electron, etc., etc. So, I mean, the real conclusion of these lectures is that there is no conclusions. There are observations that kind of pull you in different directions, and it's up to you to choose what path you want to walk on, and that will determine whether you win a Nobel Prize or you write models that are not realized in nature.
Okay, so thank you, Raphael.